Okay, today we're talking about electric fields, and we'll be able to describe the difference between electric force and electric field, discern which equation to use to calculate the electric field, and determine the direction of electric force and the electric field. Boom, there you are. Okay. Did you guys notice as you walked in the space in here? It's weird. Did you guys see that? Like, folks, you like passed right through it. Did you feel that? You're like, whoa. Okay. Check this out. Okay. Tennis ball has mass, right? Okay. Therefore, it has inertia. I'm going to stick this tennis ball at rest. What does its inertia want to do? Stay at rest. Watch this. It's been doing that all morning long. It's just the craziest. It's like no strings, no nothing. It's as if something like comes off it. Weird. Breaking character. That's gravity. All right. So in this location, is there a force of gravity? Yes. If I take this tennis ball away and I get rid of all the air molecules, it's just this space here. Is there a force of gravity in this location? I would say no. There's not a force of gravity, but there is a gravitational field at that location. Because in order to have a force of gravity, you need two masses in order for a gravitational force. Does that make sense? You got the mass of the Earth, and then you got the mass of the tennis ball. But in order, but if you only have one mass right there, and looking at this location, there's no force of gravity. But we can say there's a gravitational field at that location. So how would I describe a field? This is a region that has a promise of a force. It's kind of a weird way to describe that, but if we stick, so we have around the entire Earth is a gravitational field. If you stick something with mass in that gravitational field, then it'll experience a force. It's kind of like the promise of, like, hey, if you go into this area, this region with mass, you're going to experience a force. Okay with that? So around the whole Earth, there's a gravitational field. You weigh something, there's a force of gravity on you because you have mass inside the Earth's gravitational field. Is another way to look at it. Okay? So I'm going to use that to introduce Van de Graaff generator. The Van de Graaff generator. Here's what this is. You've got a spool down here that's okay of letting go of electrons. You've got a conveyor belt made of like rubber band material that carries those electrons up. And up at the top here, you have this metal comb that acts kind of like a combine for electrons and harvests the electrons off of the belt. Okay, it takes those electrons by this metal tab and touches this aluminum sphere. So where on a conductor does charge reside? Where does charge go? On the outside surface. So this ball is becoming charged what? Negatively charged. Good with that? Okay. So just ignore that for right now. Okay, so packaging peanut. Ooh, right there. Okay, packaging peanut, rabbit fur, rubber rod. Okay, negatively charged. Think about what's going on inside of the peanut right now, microscopically. Okay, everybody have an idea? Now I'm going to touch the back side. Everybody know what happened to the electrons when I touched it? The charge of the peanut is now what? Is now positively charged. Good with that? Okay. We often refer to this as a test charge. It's a small charged object, usually positively charged. Okay. So this is a test charge. This is going to act like our scout. Okay. It's going to explore this region, this space, and see if it can see if there's anything weird. Okay. So Scout. Yes, sir. I want you to go check out the area. On it, sir. Do-do-do. Looks good over here, sir. Sir, I'm getting some weird readings. What do you mean? I don't know, sir. It's just weird. Okay, well, continue on. Okay, sir. Oh, sir, it's getting weird over here. Oh, sir. Oh. What do you mean weird? I don't know, sir. I'm experiencing this force. It's just weird. Okay, well, proceed with caution. Yes, sir. Okay, sir. It's getting really strong here, sir. 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 It's so weird over there. What's going on? I don't know. It's just a lot of force. Oh, come! Scout. Come in, Scout. Man down. Okay. Pretend, if you will, I should have prefaced this first. There was a curtain in front of this. So you couldn't see what was behind here, what was causing the electric field. This area in here is weird. You see it? I don't either. But we know it's weird because when we stick something with charge in this space, in this region, in this area, it experiences a force. Does that make sense? So what we would say is around this area is an electric field. It's a promise of a force if you take something with charge and you place it in that electric field. Okay? The cool thing with an electric field is you don't need to know what's creating it. All you're doing is taking a scout, a test charge, and exploring this area, and it's like, yep, weird. Yep, weirder. Well, not as weird. Like, and you're just kind of getting the lay of the land. You don't even need to know what's behind this curtain. You okay with that? Okay, electric field. That. Nope, it's good. And we will interact with that in a lot of ways in the next couple days. All right. So electric field, how would we describe it? Electric field is the promise of an electric force if a charged object is in the space of the electric field. Okay. Electric field is the promise of an electric force if a charged object is in the space of the electric field. Okay. A quick point here, once you get done copying that down. Some people get confused between electric field and electric force. Force is a capital F like always with a subscript E. Electric field is a capital E. So like, don't get those confused. Okay? Now, the way that we describe the electric field is this ratio of how much force there is for a certain amount of charge. Okay, this is the test charge, or you could say the charge on the Scout. Okay, this is the test charge, the charge on the Scout. This is the force the Scout experiences. So what I can do is I can take my Scout, my test charge, and I can test out this area. Right here, this amount of charge, this guy's experiencing a certain amount of force. Right here, it experiences another type of force. Right here, it experiences another type of force. Right here, it experiences another type of force, another type of force. And so I'm getting measurements across this area, across this region in this space. And once I have that, I can figure out, okay, the strength of the electric field is this much here, this much here, this much here, based upon that equation. And then here's the powerful part of this. I've got this area mapped out. Then I can take something else with charge. Let's pretend I had hair, and I could rub this balloon and get this charge to have a certain amount of charge. I could accurately predict how much force this balloon will experience at this location if I know the strength of the electric field. Because this tells me the promise of the force based upon how much charge I'm going to put here in this region, in this area. Does that make sense? Like I don't even need to know what's causing that field. If I know what the strength of the field is, if I know, and I know how much charge I'm going to place in that field at that location, I will know how much force will be there. Promise of a so close to being cool. It's been my life. All right. Give that one a shot. Tell your neighbor. Correct answer is B. Just like with gravity, in order for electric force, you will need two charged objects. If you only have one, you don't have a force. You just have an electric field. Good with that? Okay, so given, looking at the example with the peanut and the Van der Graaf generator, put some numbers to it. Let's say the peanut had a charge of positive 3 microcoulombs and the Van der Graaf generator had negative 250 microcoulombs. Let's say that they were 77 meters apart and the peanut experienced a force of 13.76 newtons. Okay. So read these two equations. No. Read these two questions and see if you can figure out which equation for the electric field is appropriate for each scenario. One goes with one and the other goes with the other. Thumbs up when you have a guess. Okay, this first one is going to be that. Okay. The buzzword you're looking for is what's the charge, the one that experiences or is in the electric field. You're using this. This is the test charge, strength of the peanut. Okay. versus this. We use that equation to describe the strength electric field based upon the object creating the electric field. That's the buzzword there. Okay. Where this is the charge on the object creating the electric field. And you need to know which equation to pick. Okay. So here's how this is my go-to. One of these two equations, okay, let's say here's the Van de Graaff generator. As you go away from the Van de Graaff generator, what's going to happen just intuitively to the strength of the electric field? Is it get stronger, weaker, or stay the same? It's going to get weaker. You okay with that? Strength of the electric field gets weaker as you move away. Which of these two equations describe that the electric field is going to get weaker as you move away? The first one or the second one? The second one. As the D gets bigger, the electric field gets weaker. Okay? So in my mind, this is the source. This is what's creating this weirdness of space. This is what, that's their source charge. And as you go away from that, the electric field gets weaker. So this one is the charge of the object that is in the electric field and experiences it. That's how I remember it. So you come up with a different way, it's great. Okay. So if we were to stick numbers in here, okay, the force between them and the charge on the test charge, we would find that to be something. .459 times 10 to the 6th newtons per coulomb. Okay. And if I would stick in this here, what I would find is it's going to be the same value. That I've made this problem up to describe the strength of the electric field at this location from two different vantage points. One from the scout, the other one from the source. Okay. But here's what I'm going to do on questions I'm going to give you. I'm going to be a jerk, and I'm going to give you both charges, but I'm going to give you one or the other of that, and you have to discern which charge goes where. Sorry, you need to pick which equation you're going to use and which charge you're going to use. You get it wrong if you pick wrong, and you get it right if you pick it right. Okay? So this is the one that's the source, certain distance away. This is the one in the field experiencing the force. Okay. This is the charge of the object creating the electric field. This is the one experiencing it, like it's in there, it didn't create it. Just like, whoa, this is weird. This one actually made the space weird. Okay. Good there? Great question. Technically, yes, but in the way that I'm going to frame it in this class, we're going to say the bigger one, like a test charge is always small, and the one creating it is going to be bigger, much bigger. Okay. All right. This next question is kind of dumb. What I'm getting at here is the electric field is proportionate to 1 over d squared, so it's inverse square law. So it's gonna drop off quickly. It's gonna decrease rapidly. E. Okay. All right. This is from the reading quiz. Correct answer is A. Okay. Here's how I remember the direction of electric field. Ready? Positives are outward directed fields. Okay. Positives are like sunshine. Yay! Positive, outward. Versus negatives are like, oh man, always looking at me like my life is horrible. I can't believe they're inward directed. You're welcome. Hopefully that sticks in your brain. Good. It was worth it then. Okay. Positives outward, negatives create inward directed fields. Okay. Here are two things that I find are a stumbling block with this type of way to describe electric fields. First off, there's nothing moving in the direction of the arrows. Nothing moves in that direction. It's just a way to label, to make a distinction between the field created by a positively charged object and the field created by a negatively charged object. Nothing is moving in the direction of the electric field. Okay. The second type of idea is this. It's like when you were born, your parents gave you a name, and you use that. You introduce yourself. Hi, my name is, and no one really questions why are you named that way. Like we just go with it. The electric field was named to have an inward directed field. We just went with it. It's a convention. Someone back in the history, I think Ben Franklin, I'm not positive, but suggested this and we just went with it. Positively charged objects create outward directed fields. Negatively charged objects create inward directed fields. It's just the way it was labeled. Okay. Good with that. Here's point X. Tell your neighbor. Correct answer is D. Dangerous dinosaurs. Positive creates outward directed fields. Good with that? Okay. Yeah. Mm-hmm. It's just the way they describe the weirdness of space around a positively charged object is, yeah, it's just there's so an electric field has a direction. It's a vector. So we just pick, it has to have a direction. Yeah. Yeah, I'll circle back around when we actually start applying this, and it'll probably make sense then. Maybe. All right. Tell your neighbor the answer to this and tell them why you think so. Correct answer is, you got one vote for A. A, B. Okay. Why A? Okay. You have a negatively charged object being repelled. What charge repels negative? Negative. Does that make sense? And therefore, what's the direction of a negatively charged object? Inward. The electric field created by a negatively charged object is inward. You see the train of logic there? You're going to have to use those detective reasoning skills on the worksheet tonight. Okay, to figure out, you can figure out the math by plugging in the numbers, but to figure the direction, you gotta find context clues. Okay, here's an example problem. Object A and object B are both charged. I want to know the net electric field at point X. Okay, so A is creating its own electric field here. B is creating its own electric field here. What I want to know is the total electric field. Okay, so before we dive into this, I need to figure out which of these two equations, or both, am I going to use? Thumbs up when you have a guess. Okay. Because I'm looking for the strength of electric field that is created by A at this location, and the strength of electric field created by B at this location, I'm going to use this equation twice. Once for A and then a second time for B. Okay, so I don't have a charged object here. That's what I'm focusing on. Okay, so I've got electric field, 8.99 times 10 to the 9th times 2 times 10 to the negative 6th, because it's microcoulombs, divided by 4 centimeters, so 0.04 meters squared. So that's the electric field from A. If you could calculate that, that would be stupendous. What is it? Fun fact. Did you know that you are more likely to drown when a crowd is watching you versus only one other person watching you drown? It's true. Because everybody else in the crowd goes, well, someone else will save them. If you're the only one around, you're like, I guess I'm it.
Something offended you.
So why do I bring that up? Somebody else will calculate it. I don't know. I'm not going to worry about it. Oh, that's the relevancy.
It's supposed to be a big number.
Yes.
Okay, I got the number. I don't know.
Shoot.
I'm just gonna read out the numbers. It's 1, 1, 2, 3, 7, 5, 0, 0.
Good. We're going to say 11,200,000. I know this is improper scientific notation. So one thing I forgot to bring up. So last semester, when you calculated stuff, you had an intuitive, like you could look at a number and go, does that make sense? Like, yeah, I'm not going to get a car going half the speed of light. Like, that's not a thing. I probably need to take the square root or something. This stuff, you have no idea. Okay? You're like, I don't know, big number. I don't know. Okay, let me just, electric fields are going to be large. Going to be big numbers. So if you get a big number for electric field, they're like, okay, that's in the realm of possibilities. Okay. So I'm going to find the strength electric field from object B at this location. So we got 8.99 times 10 to the 9th, 2 times 10 to the negative 6, because it's microcoulombs. And so if this is 4 centimeters and this whole thing is 10 centimeters, what's this distance? 6 centimeters. You guys are rocking. And you find that to be equal to 5 times 10 to the 6th newtons per coulomb. Okay. So those are the numbers. Okay. Now we need to figure out direction. Okay. So is this the field created by A at point X? Is that going to the right or to the left? Goodness gracious. Tell your neighbor. The field from A at point X, is it directed to the right or to the left? The field at point X from A, is that directed to the right or to the left from object A? Show me. Okay. Outward sunshine, it's going to the right. I'm just going to put that as 11. So to the right. And the electric field from B at point X is going which way? To the left. Outward sunshine. Everybody okay with that? I'm just going to make that 11 and 5 just for simplistic sake. So the net, so what I'm asking for is the net electric field. Tell your neighbor how you would calculate that mathematically. So you would say 6.2 times 10 to the 6th newtons per coulomb to the what? Right or left? Right, because 11's bigger than 5. So I subtracted. Good with that? So electric field, it has direction. It's a vector. So because they're pointing in opposite directions, we're going to subtract them. Good with that? Okay. So you'll have one of those equations or questions on your test. Not test. You'll have one on, yes, you'll have one on your test. But you'll have one on your homework tonight. Okay. All right. So let's say I take a test charge all around object A, and I find the electric field from A to be the blue vectors. And then I do the same thing for object B, and I find the electric field from B to be all the green arrows. So I got two different fields in the same space. So I want to find the net electric field. And so I'm doing head to tail here. I'm finding the resultant of the electric fields with the red arrows. Find the resultant vector. Okay with that? So, and the way we summarize those is we take this points all over the place and we kind of connect the dots and we make these electric field line patterns. This represents this. Okay, the net electric field. Okay, and I think I described how to read these on the video, but they always go out of positive, always go into negative. Electric field lines don't cross. The closer the lines are together, the stronger the field is. The more densely packed they are, the more stronger the field is. The electric field lines will always go perpendicular from the surface of the source creating it. Yeah, characteristics of electric field lines. Okay. Sake of time, the correct answer is E, no field, because the field from this, they're identical charges, they're equal distance away, so the field from this one goes this way, the field from that one goes that way, and they cancel each other out because they're equal strengths. So there's zero electric field at that location. Like the net electric field is zero. Good there? Thumbs up when you have a guess. Have a conversation. Correct answer is, so positive creates outward directed field going this way. This one creates an inward directed field at this location going this way. The resultant of those two fields, cut and paste, head to tail. Does that make sense? Correct answer is C. Good. Tell your neighbor. Correct answer is correct answer is B. 2 is positive. You create outward directed fields, and it has a greater charge because it creates a stronger electric field because the lines are closer together around 2 than they are 1. Good with that? Tell your neighbor. Correct answer is A. A is correct. The lines are really close together here. Strongest electric field. Here they're the most spread apart, and 2 is kind of in the middle. Okay, last question. Thumbs up when you have a guess. I'm going to go through this 2 different ways. First way is the way I think you'd do it. So if this is negatively charged, it's being attracted to this one and repelled from this one. The net force is the resultant of those 2 and is going this way. Okay. Here's the second way, and I'm going to encourage you to try to understand this. It's looking from the perspective of the electric field. If this was a positive, not negative, if this is a positive test charge, okay, then the direction of force will be in the same direction as the electric field. Will be in the same direction, will be tangent to the electric field lines. So Mega, this is getting to your question that you had. If this was a positive test charge, then this would be directed, the net force would be directed that way, tangent to the electric field lines. If it was right here, it'd be directed this way. If this was positive, it'd be directed this way, tangent to the electric field lines. But because it's negative, it's acting in the opposite direction, but still tangent to direction of electric field lines. So this is where the direction of electric field lines comes into play and why it's important. Okay, so if you stick something with charge in the electric field, you know not only how strong the force is, but also which way the force is going to be acting. Good with that? And that is the physics show today, kids. Got a worksheet due tomorrow.